So we've been talking about these intermolecular forces and how the strength of them affects all these different things, viscosity and stuff. What are the forces? So we're going to talk about the different types of intermolecular forces. We're going to talk about 4 different types. The default intermolecular force that's present between everything, all molecules, all atoms, these are called dispersion forces. They also have several other names: London forces, London dispersion forces, van der Waals forces. Is there another one? Induced dipole forces. I'm going to try to stick to dispersion forces because that's what your book uses. These forces are caused by fluctuations in the electron distribution that happen inside of all atoms and molecules. Since everything has electrons, everything has dispersion forces. Those electrons, as we've learned, are kind of squirrely. They're not traveling in nice uniform orbits that are synchronized or anything. They're those probability maps, those regions where the electron probably is. And so there's a bunch of electrons in there, and they could get lopsided. They're not necessarily always symmetrically distributed around the center of the atom. So let's look at helium, which only has 2 electrons, and so that's easier to draw pictures of. So here's a helium atom at one point in time. Here's a helium atom at another point in time. And we see these electrons are kind of spread out. And then frame 3, now they happen to both be on the same side of the atom. Why? This is just random. They happen to be both over on this side. Well, that's all the negative charge in the helium atom. So all the negative charge is on this side, and there's no negative charge over here, but we've got this positive nucleus. This causes one side of the atom to be a little bit positive, not very much, just a little bit, and one side to be a little bit negative. Does that make sense? This is called an instantaneous dipole. We've talked about polar molecules, right, and how one end was different than the other because of pulling on the electrons and not sharing equally. This is something that happens instantaneously, randomly, and then it goes away again. This reminds me of one day when I walked into the living room. This was before any of my kids left for college. All 6 of them were sitting on half of the couch. I can't remember exactly what they were doing, reading a book, or I don't know, but it was like, whoa, that never happens. Right? They're usually scattered all over the place. But for whatever reason, all 6 of them together. I took a picture. I don't think it's ever happened again. Probably never will. But it could happen, right? Just kind of random. These guys are just, going along there, doing their thing, and then all of a sudden they're just on one side. It's lopsided. Instantaneous dipole, a temporary dipole. Doesn't stay very long, disappears again. Well, if one helium atom experiences this instantaneous dipole, that can affect the electron distribution in a neighboring atom. This side of the one atom is a little bit positive. That attracts the electrons over here. This reminds me of going on a blue and white cruise on the San Francisco Bay. And you're going around Alcatraz, and all of a sudden all the people on deck of the boat go over to the one side. Why? Because they all want to look at Alcatraz, right? They're attracted to it. So these electrons going over to one side of the atom to look at Alcatraz. They're attracted to this positive charge over here. That creates an instantaneous dipole in this atom and the force of attraction between the 2 atoms. It's very weak, very temporary. And then this one got lopsided, and so that caused this one to get lopsided, and these effects just kind of go throughout the substance. That is the dispersion force. One atom becomes randomly a dipole, just for an instant. It induces a dipole in the neighboring atom. There's a force of attraction. Then that guy straightens out, and it's gone. But it comes and goes and comes and goes and comes and goes. And a lot of little tiny things add up. Just think about a fly landing on your head. The first couple of times, you're just like, yeah, shoot fly, right? But it keeps coming back. And after a while, you're just ready to destroy the earth to kill the fly and make that stop, right? Little tiny things repeated over and over and over again are significant. Dipole force, dispersion force. So it happens as neighboring atoms attract each other. These are transient, constantly appearing and disappearing. How strong that dispersion force is depends on how easily the electrons in that atom or molecule can be polarized. And that's going to depend on the size of the electron cloud. A larger electron cloud is more easily polarized than a small one. Because in a large cloud, those outer electrons are farther away from the nucleus. I think of this as more like a, wearing one of those dinosaur suits or something, the inflatable suit. It's really big and kind of floppy and it's all jello-y, right? As opposed to something that's really compact and tight is not going to get lopsided. So we see a larger electron cloud will be more easily polarized, so something that's larger will tend to have stronger dispersion forces. Molar mass alone is not the only thing that determines the magnitude of dispersion forces, but we can use it as a guide when we're comparing similar elements or compounds. And I'm very selective in what I ask you to compare, especially on an exam. So if we look at the noble gases, right, these guys are similar, right? They all have full valence shells, they have their octet, they're cool with themselves, they don't interact much with others. As we've learned from atomic size trends, as we go down this group in the periodic table, the size of the atom increases. We can see that reflected in the molar mass of these atoms. Xenon has a much higher molar mass than helium. Xenon is a much larger atom than helium. Because this is much larger, its electron cloud is more easily made lopsided or polarized, and so the force of dispersion forces is stronger in xenon. We see this reflected in the much higher boiling point that xenon has compared to helium. Because what needs to happen for something to boil and go into the gas state? The particles have to have enough energy to escape the intermolecular forces that are holding them together. So strength of intermolecular force was how strong are the people in the red rover line. So helium has, like, 6-month-old babies playing red rover. I mean, you almost just look at them and they break free. Takes 4.2 Kelvin, that is just above absolute zero. That's crazy, crazy cold. But as we go here, we need to get to higher and higher temperatures, more and more thermal energy. The person has to run faster to break through the line because the line is stronger. Stronger intermolecular forces mean higher boiling points. So we see the boiling point as a measure of the strength of the intermolecular force. This demonstrates that dispersion forces increase as the size of the atom or molecule increases. Any questions? So this is the sort of question you need to be able to answer on an exam. Which hydrocarbon, CH4 or C2H6, has the higher boiling point?
C2H6.
It's the bigger one. The bigger one is going to have stronger dispersion forces. These two compounds that I'm asking you to compare here are very similar to each other. They're just carbons and hydrogens. Yes? A larger atom or molecule is going to have stronger dispersion forces. So here, that one's going to have the higher boiling point because it's larger. They are similar compounds, just carbons and hydrogens. And so what's different between them is this one's larger. The larger one has stronger dispersion forces, so the boiling point is higher. The next force is called a dipole-dipole force. This is present in all polar molecules. And this is one of the reasons that in chapter 10, we talked about how to decide if a molecule is polar or not. A polar molecule will have a dipole-dipole force. Polar molecules have permanent dipoles. It's not a dipole that just comes and goes because the electrons tend to be out of symmetry or whatever, lopsided. There's a permanent dipole present, and so there is an attraction between the positive end on one molecule and the negative end of another molecule. These are forces between molecules. So all molecules have dispersion forces. Polar molecules also have dipole-dipole forces. A nonpolar molecule will only have the dispersion force. So we observe that polar molecules have higher melting and boiling points relative to nonpolar molecules that have a similar size. Because the dispersion force comes and goes, but the dipole-dipole force is always there, and so it's going to be stronger. Dipole-dipole forces are stronger than dispersion forces. Here's formaldehyde. There's its Lewis structure. Here is a space-filling model. So we've got an oxygen here, and we've got hydrogens here. Remember my shortcut I told you, look at the central atom. If there are no lone pairs and all the atoms bonded to it are the same, it's nonpolar. This one doesn't have any lone pairs, but oxygen and hydrogen are different. This is a polar molecule. The oxygen end is more negative. Oxygen is more electronegative than hydrogen. This end is more positive. So what happens is the negative end of one formaldehyde molecule has an electrostatic attraction for the positive end of a neighboring one. And that force is always there. It's weak, but it's always there, and it's much stronger than a dispersion force that comes and goes. Any questions? We can look at how this affects melting and boiling points. Here's formaldehyde and ethane, and here these have similar molar masses, almost identical. So they should have similar dispersion forces, so that's not going to affect anything. When we look at the structure, though, we see that this one's very symmetrical. This is a nonpolar molecule. It doesn't have dipole-dipole forces. This is polar. It has dipole-dipole forces. The boiling point of formaldehyde is minus 19.5 degrees Celsius. The boiling point of ethane is much lower, negative 88. This has a higher boiling point and a higher melting point. Because it has dipole-dipole forces, the molecules are held more tightly together. And so in order for them to melt or to boil, you have to get to a higher temperature. More thermal energy is required to break those bonds. Not bonds, forces. Polarity also affects how things mix. Miscibility is a weird word. You could think of it as being mixability. Kind of sounds the same. It's not an actual word. Miscibility is the ability of a liquid to mix with another liquid without separating into two phases. Alcohol and water are mixable. They'll mix together. In general, what we say is like dissolves like. So if you have two polar liquids, they have dipole-dipole forces. Those forces of attraction enable them to like each other, communicate with each other, and so they're going to mix together really well. If you have two nonpolar liquids, they're going to mix together well. But if you have a polar and a nonpolar, it's like people speaking different languages. They're not going to mix together very well. They're going to clump up or separate into layers. Examples, pentane and water don't mix. Pentane is nonpolar, water is polar. Oil and vinegar. Oil is nonpolar, vinegar in water is polar. Oil spilled on the ocean. The oil, the petroleum product, is nonpolar, and so it stays together with itself. It's excluded by the water. They don't mix together. It's because of the different types of intermolecular forces. So we need to know how to determine whether a molecule is polar. That was like over a chapter ago, so you may have forgotten. Here's the book's method. I won't even mention it. Here's my method that works most of the time, and that's good enough. A molecule is nonpolar if both of these conditions are true. No lone pairs in the central atom. The atoms bonded to the central atom are identical or have the same electronegativity. Usually it's going to be identical.
What do you mean by lone pair?
A lone pair. Okay, so let's look at ammonia. You need to look at the Lewis structure. So here's ammonia. Oops. I can't make a dot to save my life. So nitrogen has a lone pair on the central atom. The little dots, yeah. So what happens with the lone pair then is it forces the hydrogens to be more on one side. It causes the molecule to be lopsided and polar. Yeah.
So if there was, for example, if there were no lone pairs like that, I'd be considered polar. I mean, non-polar.
Right. So if you had something like boron with 3 hydrogens, which does not have a lone pair because it violates the octet rule, this is nonpolar. Because the 3 things bonded to the central atom here are all the same, and there aren't any lone pairs.
But if one hydrogen was, like, for example, a double bond, then it would be considered polar, right?
Yeah, or if you had something like this,
Okay.
that's the formaldehyde. So something's different. Basically, this is a shortcut to say, is it a symmetrical, completely symmetrical molecule, or is it lopsided? And you really have to look at the Lewis structure to figure that out, because those lone pairs are hard. Yeah. What is with boron only having 6? Boron is one of the small elements, and so it violates the octet rule. So does beryllium, and helium and hydrogen. Yeah. So do you have to remember that? No, not really. Yes.
So on page 1 of the worksheet, it asks us to name
The major intermolecular force?
yeah. So
That's
do
going to
we
be
need
the strongest one.
So do we need to make a Lewis dot structure for each to find that out?
Well, you'll need to know if the molecule's polar or not.
So we would need to.
You may need to, yeah. You may need a Lewis structure. So determine whether or not each of these molecules has dipole-dipole forces. So this one. And that's easily misinterpreted as 4 chlorine atoms, right? Because that I looks the same as this L. I really need to go through and change the font on this, but I haven't had time. So I wrote out the name, carbon tetraiodide. So to determine whether it has dipole-dipole forces or not, we have to consider whether or not it's polar. So here we've got carbon and these are all going to have lone pairs. But those lone pairs on the iodines, those are not on the central atom. So when we look at this, the central atom carbon has no lone pairs, and all of the atoms bonded to it are the same. This is a nonpolar molecule. Does it have dipole-dipole forces?
No.
No.
So it would be dispersion.
It has dispersion forces. Those are the only forces it has.
Has what?
Dispersion forces? Everything has dispersion forces. It's nonpolar. Yeah, this is nonpolar. CH3Cl. Well, CH3, and then there's a Cl. Does it have lone pairs on the central atom?
No.
No. Are all the atoms bonded to the central atom the same?
Yes.
No, they're not the same.
So
It's polar. To be nonpolar, it has to have no lone pairs, and all the atoms have to be the same. So this is a polar molecule. Does it have dipole-dipole forces?
Yes.
Yep, it does.
Wait, are they called dipole-dipole?
Dipole-dipole
Oh, I thought
For
this was
polar
called
molecules.
dispersion force.
What about HCl?
Because it's not,
So we could draw the full Lewis structure. There's no harm in that.
but isn't it basically like a non-metal and metal with the polar thing?
Well, it's not a nonmetal and a metal because hydrogen is not a metal. But if you try to apply the rules, you're like, well, what's the central atom? Well, there isn't a central atom because there's only two. So this is a diatomic molecule. If you only have two atoms, there's only the bond between those two atoms. If the bond is polar, the molecule's polar. How do you tell if the bond's polar?
The charge.
Well, electronegativity, right? But what works most of the time is, are those two elements different?
Yeah.
Yeah, then chances are excellent that that bond is polar. If they are the same, like two hydrogens, two nitrogens, two chlorines, then obviously the electronegativity is the same. So if those two are different, I expect you to tell me that's a polar molecule. Will that always be true? No. But would I ask you a question to mess you up with that on an exam? No, I wouldn't do that to you. So this has dipole-dipole forces.
Isn't hydrogen a terminal end?
Yeah?
So can we just say chlorine will be the central atom?
Well, yeah, you could say that chlorine will be the central atom. But what if you had hydrogen and hydrogen? What's the central atom?
Oh, it's not.
Yeah.
Yeah.
It's like you can't be in the middle if there's only two things. Both things are in the end. Yeah.
Do you not need to look at the periodic table for electronegativity?
I'm not asking, in a question like this, we don't need to know which is more electronegative, which end is more negative, and which end is more positive. We'd have to look at the periodic table for that. We're just saying, are they different? Is the bond polar? They're different, the bond's polar.
Even though they're different, sometimes their electronegativity may not be.
That's
very
true.
different, so, or it may not be different at all. So
Well, like,
how would that be?
well, like carbon and hydrogen, their electronegativities are close enough that it's considered a nonpolar bond. But CH doesn't exist. There are not that many diatomic molecules. Most of them are either two atoms of the same element, or they're hydrogen in something. And so we're not going to run into those. I think, but that's ionic. An ionic compound is different. These are molecules.
But even for B, the fact that chlorine is in there, you would have to know.
Well,
I mean, the Lewis dot structure helps, but if you're thinking in terms of electronegativity.
So what I'm trying to teach you is a simple, it's like quick and dirty method. Does it work all the time? Is it perfect? No. But it works most of the time, and we can remember it, and we don't need a periodic table, and we can just, get it and go on. So do we need to know what the electronegativity of chlorine and hydrogen are? No, we don't. I'm saying if one of them's different, call it polar, and we're going to go with that.
Okay.
Okay? Could you have a molecule like this where it's actually nonpolar because the electronegativity differences are small enough? Yeah, you could. But I am controlling what I give you, and so I'm not going to give you those.
And just last thing, would you say it's the CH3Cl is polar because chlorine's holding more electrons?
Because the electronegativity of this is different than the others, than the hydrogens. It is more electronegative. This end is going to be negative.
Simply because it's different?
Because it's more just because it's different is how I say it's polar.
Okay.
The next one is hydrogen bonding. Hydrogen bonding happens in polar molecules that have a hydrogen atom bonded directly to fluorine, oxygen, or nitrogen. So this is called a hydrogen bond. You could think of it as super dipole force, like Superman, right? He's stronger and better and everything, right? Super dipole force. It's called hydrogen bonding. The reason that the fluorine, oxygen, and nitrogen bonded to hydrogen are special is because those are the three most electronegative elements, and they are also some of the smallest elements. Their atoms are smaller, and so it allows them to get close to each other, and intermolecular forces are stronger when the molecules can get close to each other.
So something like NH3 would be a hydrogen bond.
Exactly.
Bond.
Yes. So how do you remember which ones? Well, oops. No, oops again. So F, O, or N directly bonded to hydrogen. That's a bad hydrogen. It's a bad H. There we go. You guys seen the movie E.T.?
Yeah.
Yeah. So E.T. phone home. He'd point to this guy, E.T. phone home. Phone home. You can't spell. Okay, E.T. phone home, right? It works. So you have to have fluorine, oxygen, or nitrogen, and it has to be bonded directly to a hydrogen atom. If that's present, then you can have hydrogen bonding. Okay? Important to remember, hydrogen bonds are not covalent bonds. They have the word bond in their name, and so we tend to think of them as, oh, well, this would be hydrogen bonding. It's a hydrogen bonded to another hydrogen. Why isn't that hydrogen bonding? Well, that's a covalent bond between two hydrogen atoms, but that's not hydrogen bonding. Hydrogen bonding is phone home. Hydrogen bonds are between molecules. Covalent bonds are between atoms inside the same molecule. Hydrogen bonds are much weaker than covalent bonds. They're only 2 to 5% as strong as a typical covalent bond. So they're still much weaker than covalent bonds. But they are stronger than dipole-dipole forces. So let's look at hydrogen fluoride. So here we have hydrogen and fluorine, and this meets the ET phone home criteria. We've got fluorine bonded directly to hydrogen. This bond here is not the hydrogen bond. That is a covalent bond between an atom of hydrogen and an atom of fluorine. What the hydrogen bond is this attraction between the negative end of one HF molecule and the positive end of the other HF molecule. This force of attraction is not as strong as an ionic bond because these are partial charges. This isn't -1 and +1. It's partial. But with hydrogen and fluorine combination, it's larger than it would be with like hydrogen and sulfur or something, because fluorine is more electronegative. So these guys are strongly attracted to each other. That's the hydrogen bond. Methanol. Here we've got carbon with 3 hydrogens on it, and carbon bonded to oxygen and oxygen bonded to hydrogen. Phone home, here we've got the O from phone bonded to hydrogen. We're going to have hydrogen bonding. The hydrogen on one methanol molecule is attracted to the oxygen on a neighboring methanol molecule. Any questions? We can see the effect of this on melting and boiling points as well. So here we've got methanol and ethane, and their molar masses are similar. So difference in dispersion force is not going to account for the changes we see here. Ethane is a nonpolar molecule. You see how nice and symmetrical it is? Mm-hmm. It has a very low boiling point, -88. Methanol, similar in size, but here's this oxygen-hydrogen. The oxygen, if we drew the Lewis structure, would have lone pairs, but we can just see, looking at it, this is lopsided, this is a polar molecule. So it's got dipole-dipole forces, but it also has hydrogen bonding, and we see that its boiling point is 64. Positive 64, this one, similar size, -88. Hydrogen bondings have a tremendous effect on melting and boiling points. Any questions? Water has hydrogen bonding because you've got the oxygen-hydrogen bond in a polar molecule. So oxygen on one is attracted to hydrogen on the other. And what we'll see is that the boiling point of water, 100 degrees Celsius, is remarkably high for a molecule that's this small, only 18 grams per mole. It's due to hydrogen bonding. Hydrogen bonding is really important in your body. Your DNA strands are held together by hydrogen bonding. These are the base pairs that attach to each other through hydrogen bonding that hold the two strands together. Thymine and adenine will form 2 hydrogen bonds between this pair of molecules, and cytosine and guanine will form 3. And so cytosine never pairs up with adenine because they don't match up very well. Cytosine always pairs up with guanine. And so when your DNA replicates, a little guy comes through here and breaks those hydrogen bonds, separates the 2 strands, and uses those as a template to make new ones. So if you separate this strand off, what you're going to put on this blue thymine is an adenine. And you're going to go down and replicate this strand by putting the corresponding the bases on here. And then this one, where you have adenine, you'd put a thymine on there, and you end up duplicating the DNA. It's really amazing. We don't have time to talk about it very much. So which has a higher boiling point, HF or HCl? HF, why? That's a deadly question, isn't it? Well, let's look at these guys. Are they polar molecules? Yeah. They're both just simple 2-atom molecules, different atoms, right? So they're definitely polar. So what forces do these have? They both have dispersion forces, because all things have dispersion forces. They both have dipole-dipole forces because they're polar. Does this one have hydrogen bonding? Yeah, it does. So hydrogen bonding. Does HCl have hydrogen bonding? No. Nope. Because there's no Cl in ET phone home. This hydrogen bonding is a stronger force than the dipole-dipole force. So they're the same up to that point, but this one doesn't have the hydrogen bonding. This has stronger forces of attraction, so its boiling point will be higher.
Why do you have dispersion and dipole-dipole?
Because everything has dispersion forces. And both of these are polar. They both have dipole-dipole forces. But this one, the strongest force is a hydrogen bond. For this one, the strongest force is a dipole-dipole force, which is weaker. Stronger force, higher boiling point, higher melting point. Dang it. Just looked at the clock. Okay, we're just 2 slides real quick. IonDipole force happens only in mixtures. A mixture of an ionic compound with a polar compound. And the only thing we really need to be aware of this for is aqueous solutions of ionic compounds. So when something like sodium chloride dissolves in water, we've talked about this before, about the chlorine being attracted to the water and separating out. The positive ends of the water molecules are attracted to the chlorine. This is the IonDipole force. It's between an ion and a dipole. Very clever name, IonDipole force. And over here, positive ion, the water has a negative end that is attracted here. So they list these as intermolecular forces. That's kind of a new thing in textbooks. But this can only happen in a mixture. You can't have IonDipole forces in a pure substance. And then this is a table just summarizing those relationships.